You ever wonder how your GPS finds a route? Or how a social network can suggest friends you might actually know? Well, a lot of the time, the secret is an algorithm called depth first search. It's a super powerful way to explore any kind of network. And today, we're going to break down exactly how it works piece by piece. To really get a feel for DFS, let's start with a classic problem. Imagine you're programming a little robot to solve a maze. How do you make sure it checks out every single hallway without, getting stuck just walking back and forth in some endless loop forever? This is the exact problem that depth-first search was born to solve. You see, to a computer, almost any interconnected system can look like a giant maze, a city map, your computer's file folders, even the internet itself. We call these systems graphs. They're just a bunch of points or nodes connected by lines or edges. And just like a good maze, they are full of loops that can totally trap an explorer who isn't prepared. Now, the most basic idea you might have is to just let the robot wander. Go left, then right, whatever. But this brute force method, while it seems simple, has a massive fatal flaw. It has absolutely no memory of where it's been. And that's where you really see the difference. The problem with the forgetful brute force way is obvious. If it wanders into a loop, say from point A to point B and then right back to A, it could get stuck in that cycle for all eternity. DFS, on the other hand, is smart. It's systematic precisely because it remembers every single place it's already visited. So enter depth-first search. I want you to think of it like a clever detective who leaves a trail of breadcrumbs so they never get lost. It's a really elegant solution that avoids that brute force trap by adding one single game-changing concept: memory. Okay, so formally, what is it? DFS is a graph traversal algorithm with a really simple philosophy: go deep. It explores as far as it possibly can down one single path before it even considers trying another one. And the secret sauce, the thing that makes it all work, is its visited list. The simple list of places it's already been is what makes it impossible to go in circles. So here's the game plan, basically in 5 steps. You start somewhere, you mark your territory as visited. Then you dive deep into one of its neighbors. You just keep going deeper and deeper, marking each new spot. And here's the absolute key. When you hit a dead end, you backtrack. You just retrace your steps to the last intersection and try a path you haven't taken yet. Simple as that. All right, enough theory. Let's see DFS in action. Let's watch it navigate a real network. We're going to follow its every move just to see how this brilliant combo of deep exploration and backtracking actually works in practice. Here's our little playground, a simple graph with 5 nodes, numbered 0 through 4. We're going to kick off our search right at node 0. Okay, first things first, we're at node 0. We immediately mark it. Put a little check next to it. That way, we know not to come back here by accident. Now, from node 0, we look for a path we haven't explored, and we dive in. Let's go to node 1. We move there, mark it as visited, and add it to our path. We're committed to this path now. So, from node 1, we keep going, plunging deeper into the network, all the way to node 3. Uh-oh, at node 3, we've hit a dead end. Its only neighbor, node 1, has already been visited. There's nowhere new to go. So what's the move? It's time to backtrack. We retrace our steps right back to node 1. Okay, we're back at node 1, and we ask, hey, were there any paths here that I missed? And yes, there was. We find this unexplored route to node 4, so that's where we go next, exploring this new branch. So node 4 turns out to be another dead end. We backtrack to node 1. Now look closely. From node 1, we've now explored all the possible paths. There's nowhere else to go. So we have to backtrack again, this time all the way back to our starting point, node 0. And now we're right back where we started. We have one final path to explore, the route to node 2. We take it, we mark it, and just like that, we visited every single node in the graph. And there you have it. We've systematically gone through the entire network without ever getting lost. The final order that we visited each new node in was 0, then 1, 3, 4, and finally 2. So we've seen how DFS can solve a simple little puzzle. But its real power isn't just in theory, it's in the massive, complex problems that it solves out in the real world. Let's take a look at how this becomes a cornerstone of modern computing. What's absolutely amazing about DFS is its incredible efficiency. It can chew through massive networks with millions of nodes and not even break a sweat. The reason is simple. Because it keeps that visited list, it is guaranteed to only look at each node, or V, and each connection, or E, exactly one time. And that incredible speed unlocks a huge range of applications. We're talking finding a path for a character in a video game, detecting those circular dependencies in a spreadsheet that cause errors, organizing tasks for a complex project. DFS is the engine running behind the scenes in so many smart systems we use every single day. The key takeaway here is this: depth-first search is all about commitment. It picks a single path, and it follows it relentlessly to the very, very end, before it even considers another option. It's this focused, deep, systematic persistence that makes it so incredibly powerful. So you now have a powerful new tool for exploring complexity. The logic of diving deep, backtracking when you have to, and trying again is fundamental to solving countless problems. Now that you understand the power of a deep search, what complex problems will you unravel?